In this example problem, we're going to find the concrete shear contribution and the required steel per foot transverse shear reinforcement at the critical section using the following procedures. We're going to use the ACI 31819 Simplified and Detailed Procedure, and then we're also going to use the AASHTO LRFD General Procedure. So ACI 31819 is typically used for building design, and AASHTO LRFD is typically used for bridge design. So we'll use both of these. We're not going to find the actual shear reinforcement or the minimum reinforcement required or the maximum spacing requirements. In this example, I cover those in other examples. We're going to be looking at, in this example, a Florida I-beam with a depth of 36 inches and a cast-in-place deck that's composite with the I-beam with an 8-inch depth and a 96-inch width, with our 96 inches being the beam spacing, so the center-to-center spacing of our beam. I give us our gross section properties here for our FIB section, and I also give us our composite section properties. We have also shown here the section, or some other section of material properties. We have our precast concrete strength, our given modulus for our concrete, and our strand depth and strand area. And we'll have a 100-foot span length here. The loading applied to our beam is shown here. So we'll have a 1.64 kip per foot distributed dead load, and this is going to include the self-weight of the girder and also the weight of our deck. And then we also have a distributed live load, which is 1.4 kips per foot. Note here that the standard bridge loading per AASHTO HL93 includes both a truck load, which is a series of point loads, and a design lane load. Just to simplify this example, I'm lumping all these into one distributed load. So, you know, the loading's a little different than it would actually be for a bridge, but it'll serve us well for this example. So you can see here I have two different factored loads. I have our factored load with the most common load combination in ACI, so 1.2 times the dead load plus 1.6 times the live load. And I also have one of the most common load combinations per AASHTO, our strength 1 requirement, which is 1.25 times dead and 1.75 times live. So we'll have two different W sub U's that we'll use, one for the ACI procedure and one for AASHTO. You can see next that our beam has some debonded strands. So strand debonding can be used to help decrease our end region stresses in pretension girders. This beam has 10 debonded strands out of our total 30 strands, which is about 33%, or which is 33% of our total strands. And you can see that these 10 strands are all debonded 6 feet into the beam. So the 10 debonded strands don't start bonding with the concrete until 6 feet into the beam, and then they start to pick up stress. So you can see in the first 6 feet, we're going to have a different strand area than in the rest of the beam. And we'll also have to develop the strands. The 20 strands will start transfer and development length at the end, and the other 10 strands will start at the end of the debonding region. So our critical section we're going to take as h/2 from the edge of our bearing, h/2 from the edge of the bearing for ACI, and dV away from the edge of the bearing for AASHTO. So these are going to be the two values that we use for our critical section in this example. And then you can see the strand area at the critical section for both of these designs is going to be 4.34 square inches. We'll start by finding the concrete shear contribution using the ACI 31819 Simplified Procedure. The first thing we'll need to do is we'll need to find our ultimate shear demand and our ultimate moment demand at our critical section. So you can see here I find these two values. So at the critical section we have 200.3 kips for our ultimate shear, and 5,965 kip inches for our ultimate moment. We'll also need the depth of our strands of our composite section, and ACI says that the D that we use for our shear calculations for concrete and steel doesn't need to be less than 0.8 times the overall height. So here we have our actual D, 40.1, and we can see that this is greater than 0.8 times H, 35.2. So in this example, we're using the actual D for our shear calculations. We can now plug all of our known values into the equations from the ACI Simplified Procedure. So there's a table, table 22.5.6.2 with 3 different equations. And for the simplified procedure, you take the minimum of these 3, but it doesn't need to be less than 2 times the square root of f prime c bwd. All right, so we'll find our A, B, and C. So starting with our A equation, we'll have our VC is equal to 0.6 times 1.0. We have normal weight concrete here, times the square root of 8,500 psi plus 700 times our V sub U 200.3 times our D 40.1 divided by our M sub U, which is 5,965 kip inches. So we take all this times our BW 7 inches times 40.1 D, and then I'm going to divide by 1,000 pounds per kip to give us units of kips, and we'll have 280.9 kips. We can then do the same with our equation B here. So our VC here is equal to 0.6 times 1.0 times the square root of 8,500 psi plus 700 times 7 times 40.1 divided by 1,000 pounds per kip. And this will give us a value here of 212.2 kips. Our last equation here will be VC equals 5 times 1.0 for normal weight concrete times the square root of 8,500 psi times 7 inches times 40.1 inch divided by 1,000 pounds per kip. It's going to give us a value here of 129.5 kips. So we can see this 129.5 is the minimum of our A, B, and C equations. And also 129.5 is greater than our 51.8. So this will be our VC. So we'll have our VC. Note that in ACI, whenever we have a square root or another given constant, our units are PSI. So here we have a concrete strength of 8,500 PSI, so that's what I'm using in the square root. We'll notice that that's different than AASHTO. So I just wanted to point that out here. All right, so next we can take our phi, which in ACI for shear is 0.75, times our VC, 129.5, to give us our phi VC of 97.1. We can compare this to our ultimate and our ultimate shear, and we'll see that we need shear reinforcement for strength at the critical section. So we can use our equation for our AV required to calculate the amount of shear reinforcement that we'll need per foot. So our VU here is 200.3 kips minus our phi VC 97.1 kips times 12 inches per foot. So we're going to use a standard spacing here to get inches squared per foot. And then our phi 0.75 60 KSI is the yield strength of our shear reinforcement, and then our D is 40.1. So we'll get an AV required here of 0.685 inches squared per foot. So you can look at one of the other example problem videos for how to actually design the shear reinforcement for this required shear reinforcement. I'm not going to cover that in this video. We're now ready to move on to calculate the concrete shear contribution using the detailed procedure from ACI 31819. The first thing that we'll need to do here is calculate our ultimate shear demand, which we did already, 200.3. Our shear demand from the unfactored dead load. So the unfactored dead load, and our shear demand from that is 78.0. And then using that, we can find the factored shear from the externally applied loads, which is here 122.3. We need to find the same values, but for moments. So our ultimate moment, our moment from just the unfactored dead load, and also our maximum factored moment from the externally applied loads. So we'll use these shear and moments in the following design equations. For our flexure shear capacity equation, we're going to need to calculate the cracking moment at the section of interest, which is at the critical section for us. So we can find our section modulus at the bottom for our non-composite section, the section modulus to the bottom of our composite section. And next we need to find the transfer length and see if our critical section falls within the transfer length. So here we can see our transfer length is 50 times dB, so 30 inches. And we can see the available transfer length is our critical, or the length from the center of our bearing to the critical section, 29 inches, plus the other half of the bearing to the end of the beam, so 14/2, which will give us a total available transfer length here of 36 inches. So we can see that this 36 is greater than the 30, so we're kind of past the transfer length, and we'll be able to fully transfer our pre-stressing. So we can use 150 KSI for the stress in our pre-stressing at this point. So our area of pre-stressing is 4.34 square inches here, and we take that times our FPE to get 651 kips. Our strand eccentricity using our gross non-composite section properties is 12.62. We can then plug these values all into our cracking moment equation from ACI. So our cracking moment then is going to be equal to the section modulus of our composite section. So 11,889 inches to the third. We use our composite section here because our composite section is resisting that externally applied cracking moment. So we'll take this times 6 times 1.0 times the square root of 8,500 psi. I'm going to divide this by 1,000 pounds per kip to get all my units in KSI. I'm going to add in my 651 kips divided by my gross area, 806.58 square inches, plus 651 times the eccentricity, 12.62, divided by my section modulus of my gross section, 735, and then minus the dead load moment, 2,323 kip inches, divided by my section modulus, 7,735 inches to the third. So we'll get our M cracking to be equal to 25,200 and 17 kip inches. So this is the value that we'll use moving forward in this example. We're now ready to plug in our known values into our flexure shear equation. So our VCI is equal to 6 times 1.0, our lambda for normal weight concrete, times the square root of 8,500 psi divided by 1,000 pounds per kip times 7 inches times 40.1 inches plus 122.3 kips times our M cracking, which we found to be 25,217 kip inches, divided by our M max, which we found to be 3,642 kip inches, and then plus our V sub D, which is 78.0 kips. So then we'll find our V sub CI here to be equal to 940.3 kips. We can see that this value is greater than our lower limit here, 51.8. So our VCI is equal to 940.3 kips. Now that we've found the flexure shear capacity, we can next calculate our web shear capacity. And the first thing that we need to do is find our compressive stress in the concrete at the centroid of the cross section resisting these externally applied loads, or F sub PC. So our F sub PC is equal to the equation shown here for composite sections. For non-composite sections, we would not have the second and third term. We would only have the first term. So that would be for non-composite. So that would end up working its way out because your YB for your composite would be equal to YB in a non-composite section, so the last two terms would cancel. So anyway, we can plug in our known values here and find an F sub PC equal to 0.378 KSI. So this is the value that we'll need to use in our web shear capacity equation. If we had harped or draped strands, we would need to include the vertical component of our pre-stressing in this equation. So we would need to calculate our VsubP. Because we don't have harped or draped strands here, we have straight strands. Our strand angle is going to be equal to 0, so we're going to have no vertical component of our pre-stressing. So now we can plug in all of our known values into our web shear equation. So here our VCW is going to be equal to 3.5 times 1.0 times the square root of 8,500 psi divided by 1,000 pounds per kip plus 0.3 times the FPC, which we found to be 0.378 KSI on the last slide. And then we take this times our BW 7 inches times 40.1 inches, which will give us a VCW here equal to 122.1 kips. So you can see our VCWs here, we found our VCI, so now we can use those to find our VC. Our VC is going to equal the minimum of VCI and VCW. So our VCI we found to be 940.3, our VCW 121 or 122.1. So our VC is the minimum of those, 122.1. We can then factor this VC. So phi VC 0.75, our resistance factor for shear, times 122.1 will give us 91.6 kips. We can see that this value, 91.6, is less than our shear demand, 200.3. So we need to include shear reinforcement for shear strength at this location. We can calculate that using the same equation that we did for the simplified procedure, and we'll find a AV required of 0.723 square inches per foot. You can see here, I plot the shear resistance and shear demand along the length. So you can see in gray we have our detailed, blue we have our simplified, and orange we have our demand. So you can see our demand along the length. We'll need shear reinforcement for strength for the majority of the length up until our shear resistance, our factored shear resistance from our concrete crosses our shear demand. And then at this point here, we'll need minimum shear reinforcement for the rest of the beam. So that concludes our ACI 318-19 portion of this example. Next, we're going to find our concrete shear resistance and required shear reinforcement using the AASHTO LRFD procedure. So you can see we'll need our D again, which our actual D of our strands is 40.1. We'll also need for this procedure several parameters that we would get during our flexural design. So I'm just giving them to us here, but at our critical section, we're going to have a nominal flexural strength considering the development and actual area of the strands of 15,822. Our strand stress at ultimate, assuming that our strands are fully developed, is 259.6. Our strand stress considering the required development length is 163.3. And our effective stress, assuming that we can get transfer after all losses, is 150 KSI. So we can use our D then, and we can find our effective shear depth. So in AASHTO, our effective shear depth is the distance between our compression force and our tension force. The commentary defines this effective shear depth as just our nominal moment, Mn, divided by ASFY plus APS FPS, where the bottom term here is our tension reinforcement. So for us, we only have an APS FPS, so we don't have that other term. So we can calculate dV here to be 22.3 inches. AASHTO tells us that the dV doesn't or need not be taken less than the greater of 0.9 times dE and 0.72 H. So our D sub E is just the depth, the actual depth of our pre-stressing strands, 40.1, and our H is 44 inches. So we can calculate 0.9 times dE to be 36.1 and 0.72 times H to be 31.7. We'll see that 0.9 dE is the max here, so our D sub V, our effective shear depth, is 36.1. So this is the value that we're going to use to find our concrete and then our concrete shear contribution, and then also we'll use it to find our required steel. So just to highlight, ACI adds the VsubP component, or the vertical pre-stressing component, in with VC. AASHTO separates it out so that your V sub N is a combination of VC plus VS plus VP. So in this example problem, we don't have harped or draped strands, so our VP is going to be equal to 0 because the angle of our strands is equal to 0. But I'm going to go through and calculate our available strand development length compared to the required, so we can calculate our P sub P, or the force in the pre-stressing component. So our required development length, we can use our AASHTO equation, and we'll find our required development length for our 6/10 inch diameter strands to be 153.2 inches. Our required transfer length is 36 inches, and our available transfer or development length at the location that we're considering shear is 50.1 inches. So we can see that this 50.1 falls between our transfer length and our development length. So we're going to be able to get our effective pre-stress in the strands, but we won't be able to get the full pre-stressing stress at ultimate. Because we're between the transfer and development length, we'll need to use this equation from AASHTO. You can see we're plugging in our values, we'll get a actual stress in our pre-stressing at the location at our critical section to be 163.3 KSI. We can take that times the actual amount of reinforcement at this section. So 20 of our strands are bonded at this point, so we're going to count the area of 20 6/10 diameter strands. So 4.34 times this 163.3 will give us a total pre-stressing force of 708.7. So if we did have harped or draped strands, then we would need to plug that value into our VsubP component. Here we don't, so we're going to get 0 vertical component in our pre-stressing force. But again, I just wanted to kind of show you how it's done in case you do have harped or draped strands. We're going to need to calculate the longitudinal tensile strain at the section, or in the section at the centroid of the tension reinforcement, this epsilon S component. And we'll need to first calculate the shear demand and our ultimate moment demand at the section of interest. We're also going to need to either assume that we have a tensile strain or a compression strain at this location. So we're going to assume that we have a compression strain here, and then we're going to go back and check to make sure that our assumption was correct. In our compression strain, we have an additional component here to our denominator that we'll need to include. So here you can see I'm finding our shear and moment demand at our critical section. Compared to ACI, we have a larger distributed load because of our different factors, and also our critical section is a little further out. So this changes our shear and moment slightly. So we have our ultimate shear at the critical section, and we also have our ultimate moment at the critical section shown here. AASHTO tells us that the minimum MU value, so MU can be, or needs to be, is greater than V sub U minus V sub P times dV. So we can see that this term is equal to 7,538, which is less than our actual MU. So we're going to use the actual MU at this point. The other two terms that we'll need are the area of concrete on the flexural tension side of the member, and also this parameter that takes into account the locked-in strain differential between our concrete and our steel. So if you're using a computer drafting software, it'll be easier for you to find this area. But essentially, this ACT is the area in our section below the mid-height. So you draw a line at h/2, and the area below this line in our concrete is our ACT. So if you're using a computer drafting software, you can select that area and automatically find the area. Here we're going to guess that that area is about 3/5 of the gross area of our precast section. We have this big bulb T, so I'm assuming that a little more of our area is below that mid-height. AASHTO tells us for this FP naught term that is usually appropriate to use a 0.7 times F sub PU. So we're going to use that here. So 189 KSI will be our value there. We can then plug in our different values into our longitudinal tensile strain equation. So our epsilon S is going to be equal to the absolute value of 9,370 kip inches divided by 36.1 inches, plus we don't have any axial load, so 0, plus the absolute value of V sub U, 208.8 kips, minus, we don't have any vertical component to our pre-stressing, so 0 kips there, minus the area of our pre-stressing here, so 4.34 square inches. We're only considering the bonded pre-stressing at this point, not our debonded strands. And then times our 189 KSI. So then we divide this by, we don't have any non-pre-stressed steel, so we'll have 0 for our first component, plus 28,500 times APS 4.34 square inches, plus the stiffness in our concrete, 5,255 KSI, times the area here, ACT, 483.9 square inches. So we'll get an epsilon S here to be negative 0.132 times 10 to the negative third. And we can see that this is greater than the lower limit of negative 0.4 times 10 to the negative third. So this is the value that we can use for the rest of our calculations. We can then plug this tensile strain into our crack angle expression. So plugging in our tensile strain there, we'll get a crack angle of 28.5. And also our beta term, which is a factor that indicates the ability of our diagonally cracked concrete to transmit shear. So it essentially tells us how effective our concrete is at resisting shear. So we're going to assume that we have minimum transverse reinforcement. So we're going to use this left equation here. So we can calculate our beta is equal to 4.8 times 1 plus 750 times our negative 0.132 times 10 to the negative third. And we'll get a beta here of 5.33. We can plug that beta into our concrete shear contribution term then. So we'll get a V sub C equal to 0.0316 times our beta, 5.33, times our lambda, we have normal weight concrete, so 1.0, times the square root of 8.5 KSI. So note that in AASHTO, we're using KSI for our units and our square root here. And then we take that times our B sub V 7 inches times D sub V 36.1 inches. And we'll get a V sub C of 124.1 kips. So this is our V sub C. And yeah, note again that we're using KSI under a square root. In AASHTO, our resistance factor for shear is 0.9. So we take our 0.9 times our V sub C to get our phi VC equal to 111.7 kips. We can see that this value is less than our demand, 208.8. So we need shear reinforcement for strength in our beam. We're going to assume that our reinforcement is orthogonally placed, so vertically placed with an alpha angle equal to 90 degrees. Which allows us to find our required shear reinforcement per foot using the equation shown here. It's the same as ACI, only we have an additional cotangent theta term down there at the bottom. So you can see that the required shear reinforcement per foot here is 0.325 square inches per foot. Finally, we can compare side by side all of our results. So here you can see our results for our ACI expressions. So ACI Simplified, ACI Detailed, compared to the ACI Demand, AASHTO, FIVC compared to our demand. And you can see in all cases, we're going to need shear reinforcement for strength from the majority of the beam. And you can also see a comparison of our FIVC using ACI Simplified, ACI Detailed, and AASHTO side by side in the lower left. And you can see in this case, the AASHTO expression and the ACI Detailed expression are fairly similar. You can see in the table a comparison of the AV requireds that we found at the critical section. You can notice the ACI Simplified and Detailed procedures have similar AV requireds. The AASHTO general procedure has a much lower AV required. This is because in AASHTO, we calculated crack angle and we found our crack angle to be 28.5 degrees. This 28.5, we have a flatter crack than in ACI where we're assuming a 45-degree crack. So flatter crack engages more shear reinforcement, so we need less shear reinforcement per foot. So that concludes this example problem.